Hi, in this video, I'm going to talk about IPv4 and IPv6, and we're going to compare the two headers. We're going to learn about both at the same time. It's a little longer than I usually like to make my videos, but that's okay. We're going to get through a lot of good stuff. So IPv4 and IPv6, let's look at both of these together, and we're going to look at different fields. So what I'm highlighting there is kind of hard to see, but those are the fields that are similar in IPv4 as in IPv6. But there are several differences, many differences between IPv4 and IPv6 headers. First of all, the IPv6 header there in purple, you might notice is actually simpler. There's actually fewer fields. It's what we call a fixed byte header. The size of the header is 40 bytes, always 40 bytes. If you look at, by the way, if you look at the IPv4 header down here, you'll notice it has something called options and padding. This makes the IPv4 header optional, or not optional, I'm sorry, not optional. It makes it variable, meaning it can vary in size. So the length of it could actually vary in size, where the IPv6 header is always going to be a 40-byte header. All right, let's get into some of the details of this. So let's just go field by field. Version field. Okay, this is fairly straightforward. In IPv4, the version field is 4, and in IPv6, it's 6. So whatever happened to IP version 5? Well, that was an internet stream protocol, actually an experimental protocol. And it was actually just when it was carried in the IPv4 header, they changed the version to a 5. Never really used, and so, but we used up the number 5, so we had to go with the number version 6. Okay, in IPv4, we have something called the Internet Header Length Field. Okay, that's because and what it is, it's the measure of how many 32-bit words, and what I mean by that is how many of these 32-bit chunks, there's a 32-bit chunk, there's another 32-bit chunk. Sorry about my writing there. How many of those do we have? And the reason for that is because you have these options and padding that could actually make that longer. So the IHL, the Internet Header Length, says how long is this IPv4 header? Okay, in IPv6, this field isn't needed because the header length is always 40 bytes. It's fixed. And actually, that's a great thing because that way it makes processing the IP header much more efficient because there's no calculation needed by the devices that receive the packets on how big the header is. And that means how much data is left. It's always 40 bytes in IPv6. Okay, in both IPv4 and IPv6, we have something called type of service, or in IPv6, we call it traffic class. And this isn't mandated in IPv6. It has, it's the same functionality as in IPv4. And basically, it is just a way to provide quality of service. I won't go into the details here, but it's a way that we can prioritize certain packets over other packets. There is a new field in IPv6 called the flow label, and it's mostly an experimental or still in transition how it's going to be used. But the flow label is just a label given to a common stream of packets, all the packets within the same, we say, stream or flow. And it can be used to provide the same kind of level of service from source to destination as it flows through the networks. Okay, again, it's still kind of experimental at this point. Okay, let's take a look at the IPv4 total length and the IPv6 payload length fields. In IPv4, we have something called the total length field. What that is it's actually the IPv4 header plus the actual data, what kind what's ever being carried in the IPv4 packet, whichever is being encapsulated by IPv4. And it's both of these together, the header plus the data. Now, if you subtract the remember the IPv4 internet header length, you subtract that from from the total length, then you'll get the actual size of the data. Okay, the IPv6 payload length is different. It's just it doesn't include the header. Okay, what it includes is just the data itself. It also includes any extension headers. We'll talk about those in a little bit. But it's basically just the data following the IPv6 header. IPv4 fragmentation. You're going to see that there's several fields that are used in IPv4 for fragmentation. I'm going to explain what that is more in a moment. But in IPv6, there's no such fields for fragmentation. So what is fragmentation? In IPv4, what happens is if a packet is sent by a source and it is received by a router where the link, maximum transmission unit, that's MTU, is smaller than what it can fit the packet, what it can send the packet. So data links have different MTUs, maximum transmission unit, meaning how much data they can actually send across that link. Remember, data link, NIC card to NIC card communications. So think of it like getting a big refrigerator from somebody in the back of the truck, and then you've got to take it to the next point along the path. But you've just got a regular, maybe a little Miata car or something. You can't fit that refrigerator in the back of your car. So you have to actually, well, this isn't a good idea, but you got to unassemble it into smaller parts. So this is what has to happen. The packet actually gets broken up into several smaller packets, each one with their own IPv4 header. It gets fragmented. And it gets sent along all the way to the final destination, and it's the final destination's responsibility to reassemble that packet. And this is very inefficient because the router R2 in this case has to actually do the fragmentation, and the destination actually has to reassemble these. Okay, well, in IPv6, there is no fragmentation. What happens in IPv6 is if a packet is too large to be delivered by router R2 in this case, across its link with R3, it actually drops the packet, sends a message back to the source and says, hey, the packet's too big. I need you to send it in this size of a packet. Then the source can then send that packet and the rest of the packets to the destination in the data in smaller packets. Less data per packet. And that way, no reassembly is required by the destination. Okay, the IPv4 protocol and next header fields. If you might remember in Ethernet, when we talked about the type field that says what kind of data is the Ethernet frame carrying, IP has a similar field. IPv4 calls it the protocol field, IPv6 the next header field, but basically what is the data that is being encapsulated by IP? Okay, so in IPv6 we call it the next header field. And these are some of the common values: 6 if it's a TCP segment, 17 a UDP segment, and various others. Okay, time to live, hop limit. So in IPv4, we have something called the time to live, TTL field. In IPv6, it has the same function, but just been renamed to be closer to what actually more descriptive of what it does. It's called the hop limit. So what happens is the source of every packet, whoever creates the packet, that operating system sets a time to live. Okay? And as it goes through each router along the way, the router decrements this field by 1. If it gets to 0, the router actually drops the packet. Why is this a good thing? Because it keeps packets from looping, or if we have what's called a routing loop, which is usually due to convergence issue or misconfiguration in the network, but packets going from router to router to router, let's say the same 3 routers continuously, those packets can be there forever until they saturate the link and we have to reboot the router or disconnect the links or whatever. TTL will actually, the routers will eventually drop these packets when the TTL or the hop limit gets decremented to 0. We'll also see the use of these fields in something called a trace route later. Okay, the checksum field. So IPv4 has a checksum field, IPv6 does not. A checksum is a way that a device, in this case IPv4 process, can do some calculations to see whether or not there's any errors in transmission. In IPv6, you know what we do checksum in the data link layer, and also the data that we're carrying, whether it's TCP or UDP, they usually have a checksum. So what do I have to do? It's just, to make things a little bit more efficient. We don't have to do the error checking at every layer. So what that means, by the way, I mentioned both TCP and UDP have checksum fields, as you can see there. And actually in UDP, the checksum is optional for IPv4. But because IPv6 does not have a checksum field, when UDP, let me go back here, we go to see the checksum fields there, and we have one here for TCP. So they'll do the error checking, but this is actually optional in when carried over IPv4, because IPv4 has a checksum. But when carried over IPv6, this checksum field is mandatory. Okay, so it has to be done when the UDP segment is carried over IPv6. All right, maybe a little bit more than you needed to know at this point, but it's all good stuff. This is a really nice YouTube video if you want to know how checksums are calculated. Kind of a cool little video to look at. Okay, source and destination addresses in IPv4 and IPv6. We have source addresses and destination addresses in IPv4 and IPv6. One thing I want to mention, let's see if I mention it here. Well, IPv4 is a 32-bit address. IPv6 is 128-bit addresses. Some significant changes in IPv6, and we'll talk about that in later videos. One thing I want to mention, source address is always a unicast address. It can only come from one device. The destination address can be unicast, multicast. In IPv4, it can also be a broadcast. Talk about addresses later. Options and padding, that's not used in IPv6 because it's a fixed length header, but this is what makes the IPv4 header variable in length and also makes it less efficient in processing. Okay. In IPv6, we use something called the extension header that I won't go into any detail here, but in IPv6, it is a fixed length header of 40 bytes. And that's much more efficient. Fixed length fields are always more efficient for processing. All right, I hope this gives you a little idea of both IPv4 and IPv6, looking at the headers of both, and at the same time being able to do a little bit of comparison.